whatnot, and that's what we're going to do in this case. Okay, so first of all, let me start off by saying thank you very much for coming. That you're interested in Fly to Learn means you're interested in kids learning engineering and using aviation. And my name is Tom Dubik, and I would really appreciate, like I said, you coming in your involvement with kids' education, and particularly in engineering. The company was founded by myself and Randy Witt. Randy is with Laminar Research. He's an engineer there. He's also a part owner of the company. And this company was Fly to Learn was formed when he was very interested in kids learning about engineering, and I was using X-Plane and wanting a curriculum, complaining frankly to Randy, you don't have a curriculum. Randy calling me back saying, well, if you want a curriculum, what would it look like? And so I told him, and next thing led to another, and we started working on what's now Fly to Learn. It's been a great, you have a teacher and an engineer going through this together, so we feel pretty good about the content and the approach, the educational approach we took on building Fly to Learn. I should say I've been nearly 25 years of teaching engineering to middle school and high school kids. Let's talk about what engineering is. Webster's dictionary defines engineering as the practical application of science and mathematics in the design, construction of machines, physical structure, roads, and systems. So this, and another way of thinking is, this explains to kids why they need to take science and math. Folks, we live in a time that's changed. The ball rolling down the ramp to teach acceleration is just not going to cut it with our kids. Yes, there will be a small subset of people that will look at that and be amazed how Newton and early science were able to figure out our laws, physics and laws of the universe. But that's a small fraction of the population at hand. We need to keep the things relevant and keep them interesting and keep them engaged and challenge them, academically challenge them. So, just besides, not even just Fly to Learn, but so why do we teach engineering in schools now? It's increased students' interest and exposure to science and math. I think if they go through a good engineering class, there's no more questions about why do I need this science or why do I need that math. We try to stress in this, the first 5 lessons are on science, the last 5 are on engineering. Throughout it, we're using math, and we're stressing trying to use math when it helps, trying to use math in a very relevant way, so it helps them do the simulations. They see math as a tool. Therefore, we need to prepare kids for college, be it 2-year, 4-year college. If they see it and they're motivated at an early age, they're going to want to pursue those careers. We want to promote STEM careers. Right now, there is a dearth of people that can do some of these technical jobs, while we have our unemployment just slipped under 8% recently. So this could go a long way towards improving our economy. And in the long term, those areas that have the most technological innovation tend to keep creating good jobs. If you go to Silicon Valley, you go to Boston right around where there's a big tech center there. If you go to Raleigh, Durham in North Carolina, places where they have a lot of technology being developed, they tend to keep people employed. That's not just in the near term. In the long term, we believe half the jobs created in the past were due to that. All right. The next part of this is create the next generation of aviation professionals. I go to Oshkosh every year, and I was amazed to see that we had the average age of a pilot in this country is 56 or 57. Folks, I'm 53, and I'm on the young side of your dichotomy. That's a problem. So we want to do that as well. And the final reason for doing this, and I'll get back again, is jobs. I'm going to just re-stress that we need to get people into engineering. Manufacturing is returning to the United States. It's a different kind of manufacturing than we were when we were kids. It was, you don't put a bolt on a wheel in a dirty factory. Now you're one of 2 people running a line that used to be 30 people. It's an immaculate place because you're keeping it running. And this also, when we talk about engineering, I want to be clear on this too. We're not only talking 4-year qualified engineers and programmers and applied mathematicians. We're also talking about tool and die people. We are talking about all the tech support people that go through this. We're losing those skills. They're retiring out and they're going away. The important part here is we can increase those jobs. We just can't lose the skill base. That's the important thing here. We can, if those people that can do these things leave and then move offshore, that's a lot harder to bring it back. And people are saying, well, it's salaries. Actually, it's automation now, and we can compete with automation. So what were the goals of Fly to Learn? And I pardon for this death by PowerPoint that seems to be going on right now. It'll be brief, and then we'll get into the program. We wanted something that was engaging. As I mentioned earlier, the ball rolling down the ramp, us just lecturing about engineering and not doing it is really not teaching the kids. I suggest that if you are teaching engineering and you're speaking about it more than once a week, where you're giving a full hour-length lecture, you're doing it wrong with middle school and high school kids. At the same time, you need to maintain some academic rigor here. What I mean by that is there have been some really neat programs where they get to design and create engineering, or they're doing engineering, and they say they're doing engineering. My beef with that is if the kids aren't doing science and they aren't doing math as part of it, and it's not academically rigorous, then we're setting them up for a heck of a surprise when they hit college. You know, college and maybe some classes, and some colleges I should say, and some high schools certainly, when we talk about engineering, we don't make it very engaging. Well, if we don't make it academically rigorous and they get to college where it is going to be academically rigorous, they're going to have a tough time. And something that we've been really discovering, that when you go off to college, our kids are used to grade inflation in many high schools. Most engineering schools and math programs, they never got the memo. They didn't go through grade inflation. So there you could be a very successful engineering student and you're liable to get some C's. You may even get a D in a class. I think sometimes our students get into the engineering programs, they get the first C in their life, and they bail because they're afraid they can't do it. And that would be a real shame. So we want to get them, we want to do things that are both engaging, and I found if you keep it really engaging, you can make it academically rigorous, and they will come with you. Obviously, we're teaching math and science here. Fly to Learn, the first half of it is math and science, and the second half is the engineering principle that's used the math and science they've been working on. All right, just double key that, but stress is both a scientific and engineering method with an aviation theme. Stress is both the science and engineering methods aviation theme. And by we get to the third webinar, we'll talk a lot more about what the engineering method is. But most of the kids are familiar with the scientific method. They're not familiar with the engineering method. One of the couple things that engineering methods and engineers worry about that maybe you don't worry about in science so much, that's terms of resources, time, and money. Yes, I understand science people have to write a grant and they have to come in within the grant, but that's not necessarily for profit. Whereas engineering, we worry about those resources. There's also an iteration process in engineering. You prototype, refine it, test it, prototype, refine it, test it, and then you release it to the marketplace. In science, it's repeated, but it's not that kind of iteration. Also, science tends to be good science, science done well. It's an open process. By the end, you have a peer review and everybody looks at it. In the engineering method, it tends to be more in-house, and the marketplace tells you if you did well or not. What we did, wanted to make sure our goals for this too, was not to require special equipment. I've been there, done that, where we had joysticks in the class, and all you have to do is have a joystick go bad in the middle of it, and you've got 19 kids flying in your program, and one child just saying, I can't fly, and then you spend your time trying to get a joystick working. And that's not what this is about. Our first goal is to teach engineering, second goal is it's aviation. And explain that we use with Fly to Learn flies just great with a mouse. We also wanted to run on older computers found in most schools. You know, when I started, they were saying, well, X-Plane 10, 9 will run on, any new computer, and X-Plane 10's coming out will be great. And I think we realized is a lot of schools either have older computers or they've gotten the cheap netbooks with the cheap graphic. They might be great computers, but they have a cheap video card. Because honestly, most schools, they're using computers for word processing, spreadsheets, searching on the web. They don't need that. So we wanted we use X-Plane 9, and we also make X-Plane 8 now available if X-Plane 9 won't run on your computer. Finally, because we're using X-Plane 10 is out right now, because we're using 9 and 8, we were able to license it very cheaply so we can make it very affordable. There's some fabulous engineering programs out there. The challenge is, can you make a great program, great engineering program that schools can afford? I went to a public high school in rural Ohio. It's a great school, good teachers doing the best they could, but we didn't even have AP classes. So I was particularly sensitive. I'm fortunate. If you look me up on LinkedIn, you're going to see I work at a private school here in Charlotte. It's a fabulous place. I've sent my own children there, and it's wonderful. But I want more than just the kids in affluent schools to have the means to do engineering, and that was one of our goals. Okay, let's talk about Fly to Learn itself. All right, Fly to Learn consists of 3 parts. X-Plane 9 or X-Plane 7, we're probably going to move into X-Plane 8. Right now it's 7. Fly to Learn students and teacher lesson worksheets. They've been tested like crazy. I think we're on revision 28 or 29. And we keep trying to improve them. Your feedback, you make suggestions, we're all ears. We just want to make it better. We also include presentation materials. So, for example, we have PowerPoint slides. They also run on our Keynote. We have videos, lesson videos, a short video, 3 or 4 minutes, introducing the lesson, the concepts we want to cover in lessons. It might go 5 to 8 minutes. The how-to videos are very specific, like how to take off, how to land, just very shorter videos that are very specific, to function specific. And finally, we're doing webinars all the time. So we can help that way as well. And obviously we can come, if it's a group of schools, sometimes it makes sense for us to come to a large group, when there's several teachers to be trained, to come in on a Saturday and just knock it out in 3 hours. All right, so what exactly is X-Plane? It's a flight simulator that's used by professionals. And the reason that is the way it works. And I just want to take a second to explain this, because then you can see why we can do the labs that we're doing here with X-Plane. I couldn't do with anything else. For years, I've been teaching engineering, robots, bridges, flight. I would teach the kids how to fly the flight simulator, and yes, that's applied math and science. But what I always wanted to do was change the wing and the plane fly differently. And most flight simulators, including Microsoft, what they did is they went out and got a 172 plane. They flew it. They collected lots and lots and lots of data. And so they said, if you push the throttle in this 4R and you're at this altitude, the altimeter is reading this, what will the plane do? And they collected data on that. And they put all the data into the computer, and they made a very good, pretty realistic simulator. Austin Myers, who developed X-Plane, approach was different. He was an aeronautical engineer, not a programmer. He's also a very good programmer, but his background was aeronautical engineer with a real passion of flight. And his strategy was this. I'm going to look at each piece of the airplane, cut it up. I'm going to apply all the laws that we know of the aerodynamics on each particular piece, see how they should be behaving, and then put them back together. So if you put the dimensions in for 172, provide them information, the computer calculates, hey, that wing moving through the air, this kind of horsepower, these things, it's going to fly like this, which gives you a very accurate flight simulator. If you design a rock, if you put a rock in there, it would fly like a rock. And so what he also included, because he did it this way, and this is the secret sauce, frankly, is PlaneMaker. It allows you to design and build and fly the virtual airplanes. Folks, this isn't a toy. They literally use this by Boeing. They use it, Gulfstream uses it. Burt Rutan, who's probably the great aviation aerospace designer of our generation, uses this. They all use this as a proof of concept. Now, Boeing went out and built their own Dreamliner simulation software. But they first tried out ideas, and other people would try out ideas on PlaneMaker and fly it in X-Plane. And this is real important for the science teachers listening and the engineering teachers. The new National Science Standards coming out, they want you to model. Modeling needs to be a part of your engineering process. As I had one professor explain to me this summer, he said, if you're not modeling it, simulating it first, and then building it, you're not doing modern engineering. Nobody's going to build something unless they put it in a simulator and tried it out to try out some ideas, check out what their concepts are, their proof of concept. Then we go out and build it. For years, and I still do, and we still in this program build model airplanes. But a lot of times the kids don't, it's the first time building a model airplane, so the plane may not look as good as you like. Well, is it their design that's the problem, or the way they built their design? This solves all of it. The curriculum itself is 10 lessons long. Okay? First 6 lessons are more of a science thing. This makes it lend itself very well for forces and energy. The final 4 lessons are an engineering thing. Aspect ratio, wing loading, power loading. And then the final 10th lesson is pretty amazing. And that is, as you're practicing the STEM skills, you're going to do data collection, you're going to do data analysis. You can all do this inside the program. We have the kids graphing, we have them filling out tables. The thing you're going to get to do that the kids very rarely going to get a chance to do in any kind of design, they're going to look at engineering trade-offs, and then they're going to design an airplane in the final lesson and fly it. And that's what makes it neat. This, you have the kids by the 10th lesson are doing a lot of math, they've done a lot of science, and they get to design the plane. And this program has worked not only with my kids at Latin, but kids that are at schools that are on 87% free lunches. Kids where you got 2 kids, frankly, 3 kids to a computer, and they're all into it. Okay? Now, what does a sample FTL lesson look like, fly learn lesson look like? And I promise you, this death by PowerPoint is going to be ending pretty shortly here. You have an introduction by the teacher. You have a short video. Have the kids watch that video. Have they hand out the kids the worksheets. Make the kids, or ask the kids to please read the worksheets before you get them near the computers. Because they're all going to want to fly it. They're all really super excited. And then you do the fly to learn lesson plan you're talking about. I would say in the first lesson, you might just let them fly it, let them crash the airplanes a lot, so then they'll listen to you. Especially some of our male students who are very confident and think they know everything, and really, why are you even there? You're in my way. I play this. I know about flight simulators. And some of them do know a lot, but they don't know the science and engineering underneath it for the most part. Here's the curriculum. Table of contents. Wing, first flight, may the forces be with you. We get lift, what is drag. And then they're in this too. They learn how to use the software. Thrust and stability. Then we get in the engineering side, aspect ratio, wing loading, power loading, and airplane design. Figure on average a day of class. So in the first lesson, they've watched the video that shows them how to take off. Then we ask them to read this. I've got a tip there too. I don't just answer a question, Mr. Dubik, how do I do this? I ask them, where in the readings are you confused? Show me at what point you don't understand, and I'll help you at that point. Because what you're going to find is, it tells them there. It shows them. It step by step says, do this, this, and this. The kids just don't want to read it. After they get through the first day of starting to look where it is, they pick it up pretty fast, and they don't need to really ask you so much about how to use the software. But I would really, that's another tip I have. Have them show you in the handout the part they don't understand. Now, if you do find another error in the handout, please email me and I'll get it fixed right on the spot. I am amazed how many times we've looked at this, and you still will find things occasionally. All right, this is where everything's happening. And I'll go online and show you this as well. It's called the Quick Flight Setup. And the Quick Flight Setup is right, you can see it right here. It's under Laui. That's where that picks the airport we're going to use. We use Laui because Laui is in Innsbruck, and two big mountain ranges, one to the left, one to the right. And big mountains are going there. So it acts like a fence to keep the kids flying in the same way. And in fairness, the kids, when they're first flying, they don't know where things are. I am not a pilot, but I have soloed, and I was amazed how much I got up in the air and I didn't know where I was. By the way, it's still the coolest feeling going. If you ever a chance to do it, I would really recommend it. Fly a small private airplane, it's neat. And taking off flying is just a sense of freedom. It's just like you felt when you were 15 and you got to drive a car, or 16 by yourself. It's the best. The aircraft below here is a Cessna 172. We open aircraft to get to it. It's the plane we're going to use throughout most of this. You can set the time at 8 o'clock, and we click on the CAVOK. This is where we clear up the sky. I'm going to take a moment here. Does anybody have a question? Go ahead, raise your hand on the software. See if you have any questions. Okay, so that's how the screen looks. All right. Now, when you go to take off the airplane, there's really 3 steps to this. First, you pause the airplane, and when you hit pause, the little P, white P comes up there. This brake light, you're going to click on that, so the brake is so turned off, and then you're going to push the throttle in, completely in. This black knob here is the throttle. Sometimes you have to use the down arrow key to see it, but right there is the throttle. Okay? That throttle always is full in, full blast when you go to take off. It's like flooring the car. And in fact, you can see right up here, the throttle was pulled out when the brake lights. I pushed that both again. I put it in there. Then up at the top, you click up by the pause sign and you unclick the pause, but you're going to see a white square comes up. That white square is where you're going to fly when you fly in the airplane. You're going to keep your cursor right in this white square here. You can see, just make it out here. Okay? Now, what we do in the first lesson, and this should give you a sense of what we're trying to achieve in this lesson. It's a lesson on how to take off, but it's really more of a lesson on potential and kinetic energy. That's what we want the kids to really work on. So we show them, and this is explained in the video, we show them the 6 major instruments, but what we do is we have the kids, these 3 are real important instruments. There's your airspeed, this is attitude telling you if you're going up or down. A lot of blue, you're going up. A lot of brown, you're going down. An altimeter tells you how high off you are of sea level, not off the ground. That's an important difference. In this one particularly, Laui, they're 1,900 feet off the ground. They're 1,900 feet above sea level, but 0 feet off the ground. So we get the kids to talk a little bit about that. If you're teaching weather, it's a good time. This uses a barometer to tell the airplane, hey, what's going on? But what really happens in this is we have the kids fly the planes level, then they point the nose of the airplane down. And what they end up doing is the airspeed goes up because the nose is pointed down, it's going towards the ground, airspeed picks up, but you lose altitude because you're not allowed to touch the throttle. Then they fly and then they fill out the instruments. They fill out the instruments for level flight, then they point the nose down. Then they freeze it, they fill out the instruments again with the nose pointing down. What happened? Usually after a few seconds, they're going to see as their airspeed's gone up and their altitude has gone down. Then we say, well, pull the nose up and fly and pull it up for 3 seconds. And then they pull the nose up, they go 3 seconds. And what they realize is now the airspeed goes down, but they've gained altitude. So this is a perfect time to discuss potential kinetic energy It talks about that energy can't be created, destroyed. It just simply changes forms. We have this, I've done this with 5th and 6th graders. They can tell you by the end of this, hey, why is it dangerous to be low and slow in an airplane? And you get into it. It's just, there's no energy for the plane. If you're flying low and slow and you come up to a tree standing in your way, what are you going to do? You can't go up. You're too low. You're too low to avoid the tree, and you're too slow to pull the nose back, because if you pull the nose up, you're going to bleed off some more airspeed. That's why these people that try to put out forest fires in these big military aircraft, they're huge. It's very dangerous. I'm in Charlotte, and the Charlotte Air National Guard here is one of the few centers for doing that. And we lost a plane and most of the crew this summer, because the plane has to slow down so much and get so low to the ground to drop the fire retardant. They're in a very dangerous stage. And in this case, there was the atmosphere where there was drafts forcing everything down. If they were going fast enough, you can fly through that, but they weren't, and they just got smashed straight down. So it was very, very terrible tragedy. Okay, now this is going to be the second lesson here. Before we go on to that, I'm going to go ahead and bring up X-Plane so you can kind of see it. Now, I'm just going to set things up. The X-Plane runs at a very high speed, and when we try to run it across the webinar software, it doesn't always pick up very well. But I still think there's a value of seeing when X-Plane comes up, and I can at least show you the menus. And I'm running another monitor and computer on my end, so I get a sense of what you all are seeing. Yeah, there's definitely a lag on my computer and yours. All right, a couple things I want you to see. There's the brakes. Like I said before, I don't know if you can see the mouse there. It's going to take you a second, but you see the mouse right there where the brake light is. Okay, I'm going to hit pause on my computer. It should show up in a minute. There's the pause. I'm going to come down. I just turned off the brake. I'm going to use the down arrow key to bring up my screen a little bit more. You may or may not. I'm going to bring it up some more so that we can see it. All right, good. Now I'm going to shove this throttle in. Because I'm paused, it's not going to do anything quite yet. Then, and you might not have seen it earlier, and this is why we're doing it right now. I'm going to click up here. See that square? That's your control surface. Don't let the kids put their mouse way out here to the left or way out here to the right. It's really, this is the most amount they need to turn. Okay? Then, if we hit on pause, the plane a lot of times is going to pull one way or the other before it starts going down the runway. I'm going to pause this. So what this does, I'm just going to pause it because your screen's just not going to see it take off. You can take it at home. I'm going to stay inside this cursor right here. Here, remember I told you, here's the airspeed indicator, here's the attitude indicator, and there's my altimeter. Over 1,900 feet. I'm sitting on the ground, but I'm at 1,900 feet because that's 1,900 feet above sea level. Also, if I can get your attention up here, look at this data up there we can start to collect with this. Any questions? Just kind of raise your hand. I'll try to answer them. All right. I'm going to go ahead. We got a question here. Yes, Keith. It's auto-coordinated. So when you turn left, yes. People are asking, Keith's a pilot, aviation guy himself there, clearly. Your rudder pedals control your tail and correct things like, for example, adverse yaw. and then at low airspeed or as you're going down the runway, this mouse here coordinates between when the ailerons turn, the rudder also turns. We get to lesson 6, we can do it. When we get to controls, I can show you exactly what we're talking about. Okay. All right. Well, with that in mind, let's go to the, let me show you before we go. We're going to go up here to the settings. That would be all of lesson 1, by the way. You talk about potential kinetic energy, you get the kids flying, they're all very excited. It's all happy times, or here again at your classroom. And I sit there kind of sarcastic with that comment, but it really isn't. I have kids that run to my classroom, and I have to chase them out. I don't rarely do I have to go looking for kids, if ever. And many days I have to chase them out of the classroom because we get to do a lot of neat things, including this. All right, so we have quick flight setup. There's your menu choice. Watch when I go down here, you don't see the menu. It's gone. But when I put my mouse up there, it pops up. So if you're using it and you're going, hey, where's the mouse? There it is. Then you hit settings, and then you go to that quick flight setup screen. There it is. So that's how you get to the quick flight setup screen. Now, this is what we're doing in lesson 1. In lesson 2, we get into, and I'll show you on the computer now, and then we'll do the handout, and you'll kind of see it there. We start to get into data input and output. From here, you can see the kinds of things we look at. I'm going to just check this out. There's 131 things, data marks we can collect, 131. So a lot of times we look at speeds, can be something we'll follow. We'll look at distance traveled, and then we will look at landing gear vertical forces. The reason we do landing gear vertical forces is let's go back and look at our airplane. I'll explain it that way. Okay, I'm going to hit the A key. You can see the plane here in a second. Give you a minute here. It's catching up. Again, X-Planes flies a lot faster than that. It's just the way they are. All right. Those 3 landing gear, if the weight of the planes with fuel and everything's 2,000 pounds, let's just make that number up. Or to keep the math easy, 2,100 pounds. You have these 3 landing gear here. And if they were spread across equally, then there would be something similar to, imagine, 700 pounds on each landing gear, which is not the case, but we're just using it for our example. The landing gear, there's a force going down on this landing gear. The landing gear is pushing up, and there's the force of the runway pushing up in the opposite direction. So if the weight of the airplane is coming down this way, then the runway has to push up in the opposite, or the plane would sink in the runway. So what that says is that puts a gear on the landing gear forces. And so we track that. And when the landing gear forces are 0, that means the airplane is off the ground. So it's a great way for the kids to see that. It also gets rid of a lot of confusion on what's going on with the airplane and when you took off and when you did. Now I'm going to move this around. Hopefully you'll see this. You can see it on the prop. There it is. You see the little green lines? You can barely make them out there. That's actually lift on the wing. And this is the, you can see that the prop is acting like a wing. It's spinning around here. The little green lines show lift. That's another way, just real quick visually for the kids to see how much lift is going on in the airplane. And we're going to end up using that later in our future lessons. All right, look up at the top of the screen here. You can see true airspeed, distance traveled, landing gear. Okay? Now, I'm going to run this just for a second. I'm going to go back in the cockpit and run it just so we get some data to look at on our graph. Sorry, it's not going to look good on your end, but let's just go ahead and run it. Purposely not a very good takeoff. All right, pause. Now look at my landing gear forces. They're all 0. All right? I could, let's just do this, in fact. Let's go, let's use the real plane with the real jump right here. Let's look out here. Give it a minute. There's my landing gear. 520, 786, 780, 779. That's the force of the load on that landing gear. Let's take off. Unpause it. Let me go ahead and get full throttle. Turn off the brakes. Brakes are off. Let's get the throttle here. All right, there we go. Not so much. This is working very sloppily, so don't, it's not how it looks in the plane. So I'm going down. If you look at the top hand of the screen, you got landing gear. Now I'm going to take off. Pause. My landing gear forces become 0. Okay. Now that in itself, all right, great, but how can the kids use that? Well, let's go back to the settings. Go to data input output. Let's look at our data. Data C. Right here you can see the landing gear, 700 something. That's small number, sorry. Not much I can do to make it bigger. But right down here is when the landing gear starts bouncing as I'm starting to take off. And there it is. One bit of gear opened up, then the other two came off. So at this point is when we define, hey, this is takeoff. Now there's lots of bits of data here. You don't need all of it, so we can just uncheck them. And it really doesn't matter to me the units. It's just as long as the kids are consistent. So a lot of kids know miles per hour, so we'll go that. I would like to do it. All right. We want to try to stay V true if we can. That would be the only thing I would say. So V true right there. All right. And then get rid of these because we're not really worrying about the distance up there. All we want to do is get a distance to say feet. You do it in meters, but that's right. And you got your landing gear. So now we just have 2 lines right up there. And in case you're saying, well, which line does which? What we can do is change the colors of this and go to this and do that. So it's a great way for the kids. They can see it. They can look at their data one of 2 ways. They can graph it like there, or they can take a snapshot of one piece of data at that moment in time up in the top hand corner up here. So like I say, it's flight simulator. The kids are fun, but we really can do some really cool math and science with it. Any questions about this? All right. With that in mind, I'm going to get out of here. Just go to File. Oh, by the way, too, you can also have the computer take off. For those kids that might be struggling with flying, you can have an AI take off your aircraft. And just like in the real world, no 2 aircraft takeoffs will be identical, but they will within a range, and that you will see a difference. Because, for example, in lesson 2, we're going to add weight, and then we're going to see what that does to takeoff distance. Sorry about that. Let's go ahead and get this back up. All right, may the forces be with you. These are 4 forces that we start talking about the plane. This is really how the next few lessons of science flight, we're really going to concentrate on these. Again, we're more into teaching science and engineering here, so here's a great opportunity to teach kids about the difference between mass and weight, about what a vector is, those kinds of things. And we do that in this. Now notice when we give the instructions, we did that big thorough explanation. Now it's very much more just click, here you are. Again, in lesson 2 we have a video with it, we have PowerPoint slides, but you have this as the kids read through it. And really by the second or third day they have it down. It's amazing to me. It's us adults that have the bigger issue with it. You can change, if I showed you before, you can take off the weight. And what we do in this is we increase the payload weight of the airplane. We make it from 298, 600, 900 pounds. When you do this, lad, don't worry. It's just a trend. We don't, if it's 301, that's fine. If it's 898, that's fine. Then we set these right up there, graphic and cockpit display. Not surprising, that shows up in the cockpit. Graphical, that's where you're going to be able to graph it. Like I said, this is a real tool used by real engineers. They need this ability. They also need it to save the disk or send it to the internet. We're not worried about that. Whoops. Okay. Notice we got distance travel, landing gear forces. And then if you look up here as you're flying, yes, you could use these instruments here, but I think it's a lot better to be using where you can actually get a real snapshot and the kids really can see what's going on in the airplane. And then here's some more pictures of the lift vectors right there. The green line's vertical lift, yellow is horizontal lift. And can't really see it in this shot, but there's little reds, and that's the drag. That's called induced drag, and we have that going on. Now, if we look at this, you can see just what I showed you before. We can graph all this information. Clearly, the airplane is off the ground, as our landing gear forces are all 0. And this shows another shot when we just limit the number of lines, so not to overwhelm the kids or the adults using it. Like I say, we're teaching the scientific method here. So we're also teaching data collection. So in this case, we have a trial and a load. So we have the kids take off. They set it at 298. They take off 3 times, and then they take the average distance of that. This is a great opportunity. You could plot. You can either plot the averages, or you can have them do a scatter plot and do every trial. So they kind of see. So they learn why you might use scatter points and why you take the average of those scatter points. But if you look at the loads 298, load 600, load 900, and we look at airspeed and takeoff distances, and you see that's not our huge. The takeoff distances get longer, and it's explains to the kids. They figure it out themselves, because you can ask them, why do big airlines have to have big runways? It's all that new weight. And then again, we want them to graph it. We want to ask them questions and answer it off there. We're also, if you're doing Common Core, we're going to be developing writing questions and things for the kids to write about when they're doing this. And like I said before, as they do those lessons and things, they're going to get the 6 or 7 science lessons, and then they're going to do the engineering process. Once they do the engineering process, they can go in and design their own airplane. And so that's what you've got. So for a while, they get fired up about designing flying the simulator. Then later, they get to build an airplane. And I would recommend halfway through, we have the kids get those little $2 balsa wood airplanes you can put together in 30 seconds. And then you have them fly them. They don't fly particularly well. You say to the kids, well, what can we do to make it fly better? Well, they've learned the 4 forces. They've got some ideas on stability at that point, probably. And so they say, first things they say is, well, get rid of the drag and get rid of the weight. And can we get a bigger motor? Have those things, and they can go from a 2-second flight to 6 or 8-second flight. I've had a couple fly away on campus, get up in the wind, and that's it. And that is extremely cool when it happens. Kids a little bit disappointed their plane's gone, but everybody talks about it in almost awe tones, so it's pretty neat. I usually have 1 or 2 extra airplanes hanging there for that event, so I just give it to them. They can redo another one. And in here, the black is the wing that can modify. So what we have going on there is they actually can modify the wing of the airplane. And you can change literally everything in the airplane. There's nothing you can't change in it. Now understand, you design it like a rock, it'll fly like a rock. And with that in mind, we have an airplane flight challenge that you can use. As they get to know things, say you can even have them practice doing it after they learn how to land in the 5th lesson. But what they do is, they carry the largest payload, deliver it, and land it on an airstrip. They start in Laui, but they land it. The idea is there's some hikers, they need some supplies. you're going to fly in there. So you take the largest payload that you can take, divided by the amount of time it takes you and the amount of fuel you use. And then from there, we get a score. And it just calculates it for you right in the program. This is only in the Fly to Learn version of X-Plane. No other versions of X-Plane have this feature. And so what that makes it great for is your kids can make a contest out of it, especially as they learn more and more about aviation and flight. We, with that in mind, we really are hoping schools will join us, and the schools, homeschool programs, after clubs, whatever. We don't mind. We want kids doing engineering. I don't care where they come from. We have an aviation challenge. The kids can sit there. All they have to do is save a copy of their screenshot and the airplane they designed. So it's no, and then they just submit it. So that's no real fuss and muss and fuss for the teachers. You can go ahead and get it done. So that kind of is in a nutshell of what we cover in the very first 2 lessons in Fly to Learn. And as you can see, I would say the first lesson's a day, second lesson is a day. Third lesson, fourth and fifth in particular, I would say you could combine those for a day. There's a lot of flying in them. The kids can fly as much as you want to choose them. Sixth lesson is long, and the engineering lessons are all each 1 lesson in place. So minimum, if you did all 10 lessons, is 2 weeks. Really, I would figure building the airplanes, allowing them to do the aviation challenge, you should figure 3 weeks if you're going to do all 10 lessons.